3-2 graphs of functions. So if f is a function with domain A, then the graph of f is the set of ordered pairs such that x comma f of x, where x is in A, so x is in our domain. And the graph of f is really going to be that set of all of the points x and y that fit that function. So a function f of the form f of x equals mx plus b is called a linear function. That's really what we're used to seeing as y equals mx plus b. And that's just the graph of a line where m is my slope and b is the y-intercept. Really the value where x is 0. And then we can have special cases of linear functions, and that's where our slope is 0. And for that case, we call that a constant function where it's always the same value. So in this case, we see y equals 3, or you might see f of x is equal to 3. And that would mean that no matter what x is equal to, the y value or the output is always the same. But we don't always see linear. Sometimes we see, in this case, quadratic or to the second power. So we can do this a few ways, but the quickest way to really graph something, if you're not sure off the top of your head, is to make a table of your x values, your inputs, and your f of x or your outputs. So f of x is equal to x squared in this case. Okay? Or you could just label these x and y if you prefer. All right, so we're going to choose any x values we want that fit the domain, but there are no restrictions. I can square any number I want. So I might choose -2, -1, 0, 1, and 2, but you might choose other values, and that's perfectly fine. So if I were to replace this, really, I'm thinking, okay, -2 squared, which is going to give me 4. I'm thinking -1 squared, which gives me 1. 0 squared, which gives me 0, 1 squared, which gives me 1, and 2 squared, which gives me 4. And really, I'm just plotting these points. So I have the point -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and so on. So I'm going to plot those points, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. And I could continue choosing values. I could even choose fractional values, and that would be perfectly fine as well. But they will continue to form this smooth curve of our parabola. X to the third power, again, not one that maybe you've memorized, but that's okay. We have x, and f of x is equal to x cubed, and we can choose any values we want. There are no restrictions on what we can cube. So maybe, again, we might choose those same values, but you could choose any numbers that you want. So we have -2 to the third power. That's going to give us -8. So that'll give us the point -2 comma -8. We have -1 cubed, which will give us -1. So we'll have the point -1 comma -1. 0 cubed, which is still 0. So we get the point 0, 0. When we plug in 1, 1 to the third power is 1, so we get the point 1, 1. And when we plug in 2, we get 8, so we have the point 2 comma 8. And this starts to kind of give this curve. It's almost like a parabola one direction, and then it switches the curve. Okay. Here we have the square root of x function. So we have x. F of x is equal to the square root of x. And again, we can choose any variables we want, or any values we want, but you do want to keep in mind that if I choose a negative, I'm going to get an imaginary answer, and we only want to graph real numbers. So I can't choose anything where x is less than 0. So let's start with 0. That's really the smallest x value I can choose. And then let's pick numbers that are easy to take the square root of. So the square root of 1 is easy. Square root of 2 is going to give me a decimal. Square root of 3 is going to give me a decimal. Square root of 4 is easy. 5 is kind of difficult to do. 6, 7, 8, maybe 9 wouldn't be so bad. Okay, so we'll plug them in. The square root of 0 is 0, so I have the point 0 comma 0. The square root of 1 is 1, so I have the point 1, 1. The square root of 2 is not nice, so I'm going to skip trying to plot that. Square root of 3, also not so nice. The square root of 4, however, is nice too, so we get the point 4, 2. Square root of 5 is not a nice, pretty number. Square root of 6 is also not Great. 7 and 8 also are going to give me irrational numbers, but the square root of 9 is 3, so that's 9 comma 3. So it's nicer if we can plot the easier to plot numbers. And if I were to plug in anything negative, it would be undefined. So this is an endpoint here, and it's just going to continue off to the right. And that's because I have a domain restriction here. Okay. So you might recall from Algebra 1 something called a piecewise defined function. And it's literally something that is in pieces. This piece and this piece get put together of different graphs. So a piecewise defined function is defined by different formulas on different parts of its domain. So really they're separate pieces. So if I take a look, I'm really graphing two things. I'm graphing a parabola when x is less than or equal to 1. And I'm graphing a line when x is greater than 1. So I want to make sure that I am, keeping in mind these different changes here. Okay, so when x is less than 1, you could make yourself a table here, and there's nothing wrong with that. So let's make sure we're picking for x squared. So we have x and we have f of x is equal to x squared. But we need to make sure what we're choosing are x's that are less than or equal to 1. Okay, so we could pick 1. We could pick something less than, so maybe 0, -1, -2, -3. I think -4 is going to be too big, but we could try it. Okay, so we're going to square those numbers. 1 squared is 1, so we have the point 1 comma 1. 0 squared is 0, so we have 0 comma 0. We have -1 squared, which is 1, so -1, 1. We have -2 squared, which is 4, so we have -2. Whoops, I didn't really mean to put equals there. -2 comma 4. We have -3 squared, which is 9, so we have -3 comma 9. And yes, when we use the -4, that's not going to fit. That's okay. So -4, 16 would be another point. It's just not going to fit on my graph. So that's one piece of this. And I'm allowed to continue, even though it doesn't fit on my graph. I can continue to the left. But this stops at x equals 1, and I can't go past that point. All right, then I have to switch and use a different formula when x is greater than 1. So we're going to switch, and now my table is going to look a little bit different when x is greater than 1. So we'll have x and our f of x, but this time we're using f of x is 2x plus 1. So greater than 1, well, we still should know what happens at 1, but we can't include it as part of our solution. So we're going to use an open circle at whatever 1 is, because we're going to get really, really close to 1, just like we would use an open circle on a number line. All right, so if we plug in 1, that's 2 times 1 plus 1, that's going to give us 3. So 1 comma 3, but that is an open circle at 1 comma 3, because I don't want to include that, but I want to get really, really close to it. All right, things greater than 1, maybe 2, 3, 4, 5, that might be enough. So 2 times 2 plus 1, that's 4 plus 1 is 5, so we have the point 2 comma 5. And you could keep doing this, or you could count your slope, right? We could say that we would count a slope of 2, so up 2 over 1. Either way, it's up to you. So that's going to give us 7, so we'll have 3, 7. And when we plug in 4, that's going to give us 9. And I'm going to run out of space here. 2 times 5 plus 1 is going to give us 11, and that's not going to fit on my graph. And I'm only continuing to the right and not to the left because I want to only choose where the x's are greater than 1. Okay. Sketch a graph of the absolute value function. Okay. So this time we're going to do the same thing. Or this time we're going to graph absolute value. So it's the same concept as what we were doing before. This isn't piecewise. This is back to a normal graph. So we have x and we have f of x is equal to the absolute value of x. And we're going to choose any variables. or any values of x. So maybe -3, -2, -1, 0, 1, 2, 3, just enough to get an idea of what's going on. So when I take the absolute value of -3, I get 3. So I'll have the point -3, 3. Absolute value of -2 is 2. Is 2. So I'll have -2, 2. Absolute value of -1 is 1. So I'll have -1, 1. Absolute value of 0 is 0. So I'll have 0, 0. The absolute value of 1 is 1. The absolute value of 2 is 2. Absolute value of 3 is 3. So absolute value makes this sort of V graph. Okay. Now we also have a function that is known as the greatest integer function. And this function is a little bit different than what you're used to working with. So this is called the greatest integer function. And it's marked by these brackets around this. So what this really means is that we're using the greatest integer that is less than or equal to x. Okay. So for example, if we wanted to use the greatest integer function of 2, that would give us 2. If we wanted the greatest integer function and we use 2.3 in our input, that would give us still 2, because that is the greatest integer that is less than or equal to x. If I wanted to choose 1.999, that would be 1, the greatest integer less than or equal to x. Okay. We could even do a negative here, -3.5. The greatest integer less than or equal to, now remember where we are on the number line, would be -4. So really the greatest integer to the left of it. So when we go to graph this, our x's are really within a range here, or a domain, should I really say. So we have our x, and we have f of x is the greatest integer function. All right, so we really could start anywhere on here, but let's say we are looking at where the input is, well, -2. Let's start with that. If I input -2, I'm going to get -2. But if I input -2.1, I'm still going to, or sorry, -1.9, I'm still going to get -2. If I input -1.5, I'm going to get -2. If I input anything less than -1, I'm going to get -2. So really we'll say that we're looking between -2 and -1. Okay. So we would say at -2, I get -2 all the way up until I hit -1. So I'm going to put an open circle there, and everything in between is going to give me -2 as my answer. Okay. How about -1? If I put in -1, now I'm going to get -1. If I put in -0.5, I still get -1. If I put in -0.25, I still get -1. Everything that is smaller than 0 is going to give me -1. Okay. If I put in 0, I should get 0. And everything that is smaller than 1 should give me 0. Okay. If I put in 1, I'm going to get 1. And anything smaller than 2 is going to give me 1. If I put in 2, I'm going to get 2. And anything smaller than 3 is going to give me 2. So we call this the greatest integer function, but sometimes we also refer to this as a step function. And that's because it looks like a set of stairs. Looks like a staircase. Okay. All right, so let's take a look. This next one is